Good morning. I hope you had enough coffee today, this morning. And also, you are all enjoying the OCP summit here. Yesterday was interesting day, a lot of good stuff about AI ML. So first of all, my name is Anil Agrawal, and this presentation is jointly prepared by myself and Gada from Meta. Unfortunately, she could not make it, so you're stuck with me for the next 20 minutes. I'll try my best. And also those who are joining online and probably will watch this presentation offline, thank you for joining. So the topic is, you can see AI ML, which is a big, interesting topic of this summit. Now, AI ML is very interesting, but the topic today is not AI ML alone. It's something even more rough, difficult, but I will try to make it interesting today. And the topic is hardware fault management. And another term used is RAS. How many of you know about RAS? What does RAS really means? Awesome, great. So RAS is acronym for reliability, availability, serviceability, or in general, hardware fault management. So we'll talk about hardware fault management, some of the challenges that we faced as we were building our cluster, and what we have done so far in building this RAS solution within our AI/ML cluster. So we'll just do a quick overview of the cluster itself, very rough, quick view, and then very quickly zoom in into PCIe domain, which is something we'll talk about why we are focusing on PCIe domain here in this presentation. And then we'll talk about various fault domains in the PCIe hierarchy that can occur, and what are the various error handling solutions that we have put together to mitigate those faults. And then we'll summarize. So if you look at a cluster that this was all announced in the public also, lots of compute, lots of storage, and a lot of networking. Yesterday we heard about networking is the next computing, right? So if you look at this cluster, like more than 6,000 compute nodes, it's a huge cluster. Now if you just zoom in into just one rack on the right-hand side picture and take a look at what the rack looks like. In one rack we have two nodes. We call two compute nodes, we can call. And within each of the compute node, multiple compute engines or GPUs. So we can kind of look at this left-hand side block diagram and see there are three distinct modules. CPU module, and then PCI switches, and on the bottom is the OEM modules or the extra modules. So that's a very high-level view of one single node. One thing you will notice here is that there's a lot of PCIe interfaces and the components attached to through the PCIe fabric. So if you just zoom in into one of this root port hierarchy, root port is from the CPU all the way down, we'll find that there's a lot of PCIe devices interconnected through the PCI links. So the PCI link actually is one of the main fault domain in our AI cluster within the node. Of course, there is an Ethernet and all that other components also, or fault domains. But right now, I'm just zooming on to just one node within one node. So PCI domain is one of the major fault domain that we need to make sure that we handle any faults associated with that. The key thing here is there's a large PCI hierarchy, and therefore increased platform failure blast radius due to any kind of PCI errors, PCI link errors, or any associated path errors. So now if you look at a little bit more closely from a fault domain and the fault coverage, what kind of faults that can happen in a PCI link? Well, first thing is single bit errors, bit flips, right? Now, the good thing is the PCI spec already defines pretty good data integrity solution, and it is pretty mature technology that has been developed over time. for example, there are receive errors, detection, bad TLP, bad DLPs, and then all kind of timeout, timer concepts to make sure that if there is any single bit error in the link itself, it can be corrected. They all kind of belong to the corrected error domain. And link CRC retry, link retraining, recovery, these are techniques that are being used to manage those single bit errors. Of course, there are certain bits within the header that if they get flipped, there is not a very good solution there also. But that is handled at the design level to make sure those bits are hardened and any kind of single bit flip doesn't happen on those bits. The next bucket is protocol faults or bus faults. And they are generally uncorrected errors, either non-fatal or fatal. Unsupported requests, completion timeout, complete abort, and so on and so forth, poison TLP concepts. And the solution is containment through poison, and also a technique called DPC, downstream port containment. So those are very, again, fairly robust solutions. Of course, DPC is still a new concept, and there are lots of moving parts in implementing a DPC feature, downstream port containment, because you got to have all the way from firmware to the OS implementation. But we have done that, and for us, it worked very well. And then the last bucket is very interesting. Internal errors. Now, these internal errors are really not covered through the PCI spec. It's not really on the link. Because as the data is traveling from, let's say, root port to the end device, there are internal components, like PCI switch, for example. And what happens if there's a single bit, some kind of bit flip within the switch itself, which is not on the link? Now, that's not covered by the link, right? So how do we handle that? So there's a concept called ECRC, end-to-end CRC. So we looked at that, and we found that very useful in enabling it in our cluster. In fact, this is the one that I will zoom in on and then go a little bit deeper on this ECRC concept and how it is helpful. Now, before that, let me just talk about, in general, the link level as per the spec. If you look at, in this block diagram here, at the physical layer, there's a framing concept. 8-bit, 10 bits, and those two bits are used for all kind of framing, error detection and encoding. And data scrambling is used to ensure that there is no DI by DT kind of current impulse related faults. And at the data link layer, there's all kind of data integrity checks are done to make sure that any packet that are presented to the transition layer are good packets. And then even at the transition layer, there's the flow control, poison, and then ECRC. So these are techniques that are used at the transition layer to make sure that packets, the actual data that is delivered above the transition layer is a good data. So overall, there is a robust fault handling mechanism already built in as part of the spec, and we are leveraging on that. Now let me zoom in on to ECRC. And I'm going to give you an example here and kind of walk you through the flow. On the right-hand side in the block diagram, you'll see the actual device on the PCI device. Could be an accelerator module, and then the switch on top of that, and then the host or the CPU complex. And above that is the platform-specific error handler, which is kind of firmware, and then OS. AER is the advanced error reporting handler in the OS itself, kernel. Now, in this example, step one, let's say host is fetching a data from the device. So request comes to device. Now, device is going to take the data, fetch the data from the memory, and then send reply back with the data. Now, in that process, step three, on the PCI link between the device and the switch, there's a PCI link integrity is being checked, LCRC and all that. So there's nothing wrong there. So far, everything good. So switch receives the data, everything's still so good. But now, let's say there's a bit flip happens within the PCI switch, some internal buffers. Okay? Now the PCI switch is going to forward the data to the downstream port of the switch to send upstream, right? Now their PCI switch, step number 4, is going to recompute the what's called link CRC. Now link CRC, because the link CRC module or the downstream port doesn't know there was a bit flip. So it'll compute the link CRC as if it's a good data. And the root port on the host side will receive the packet, check the LCRC. LCRC is good. The host also doesn't know about the bit flip. So in some sense, this bit flip actually is kind of a silent error. So far at the PCI link level, nobody knows. Right? Now, once at the root port, and the step 5 is going to check ECRC also, because we have enabled ECRC. Now, ECRC is the one that is not changed by the switch. It continues all the way from the initial end device all the way to root port. Now, that is where the bit flip will be detected. The ECRC mismatch will happen here. So root port will detect it and will signal the event to the firmware, to the OS and kernel. And then now the actual, how do we take the data? Because now data actually is bad, right? So that one is something very specific to us, how we have implemented it to make sure that we don't consume the data. Or if we consume it, we know what to do after that. So that's very specific to implementation. Now, from the reporting point of view, the host is the one that detected it, ECRC error. And host is going to then signal the event through platform-specific error handler, step 6, and log it and notify it to our tooling. And the tooling will then take the machine down and do further processing. And also, it sends to the OS so that at the kernel level also, we get notification. Okay. So we make use of both events, based on who is consuming the data and all that. Okay. So this is how we have used ECRC to manage some of the errors that are not handled through the PCI link integrity itself. And we can achieve the end-to-end fault handling implementation. So call to action, consider all available PCI Express RAS features while developing your clusters. High speeds and scalar deployment increases fault blast radius, and therefore it's very important. Invest in developing diagnostics, remediation, and repair solutions for precise fault identification and minimal performance impact, very important part. And this whole thought process has been inspired by OCP fault management sub-project, which is a OCP sub-project where we join and talk about what kind of challenges in fault handling and what kind of solution we should put together. So we encourage you all to contribute in defining robust PCI Express fault handling solutions. And reach out to me for any other questions about this presentation itself. Thank you. I think there are, how much time we have now? We have some time. Any questions? Yeah.
So once you detected the error, right? What's the, like an action for this device or isolation of the specific device? What do you do? What's the threshold for your actions?
Yes, very good point. So if we detect, are you referring to the ECRC error?
Yeah.
Okay. So if we detect ECRC error, this is uncorrected error, right? So we cannot tolerate even a single ECRC error. What that means is that we need to bring the machine down. And then we can restart it and see if there's a transient event, then the problem will not happen again, and we are good. If not, then we need to take either the device out, or the switch out, or the host module out, and replace that. Is that what you're asking?
Yeah.
Okay.
I was asking if maybe you had some automated isolation flows that you might consider in the future, right? To automate the whole isolation process of what was the failure. Right?
Yeah, so there are certain things, because if there maybe the ECRC happen because maybe temperature issues or thermal issues in the switch itself or some other place, right? So we do look at any other event signaled by this machine to figure out that what could have been the real cause, right? Because just looking at the ECRC error is not sufficient to say, oh, go replace the switch, or where the exactly problem is, right? So we try to make use of those, but it's not a perfect science, right? So sometimes we don't have enough data, and we have to kind of then, but we still have to take an action. And the action could be as simple as take the machine down, reset it, and let's see if the machine, and that's all automated. This is all part of the automation what we have to reset the machine and then restart, power down and power up, and just monitor it for a while. If the error pops up again, then take the machine to repair. Otherwise, continue.
Do you see any, in your experience, do you see any correlation of embedded errors with correctable errors, like rising up or appearance of poison beads?
Not a very good correlation, unfortunately. Yeah, especially in the PCIe, right, domain. There are some dependencies. Within correctable errors, yes. Let's say receive error followed by retry and all that. But uncorrected and corrected, there is not a whole lot of correlation on the links. And in our fleet, I mean, just as a little bit insight, we don't see a lot of ECRC errors, but we do see. Okay, so this is something very rare event, but when it does happen, this could be a very challenging problem for us because this is almost like a silent error, and silent error is not acceptable at all. So therefore, even though there is a performance impact, which I didn't say, but we still took the heat of the performance loss because we have enough headroom. Still, we went ahead and enabled ECRC.
Are there any numbers to quantify the probability of this event?
Not really. Yeah, it's very rare event. Yeah, but we do see that. Any other question? Good. We are doing good in time. I think we have 3 minutes or we are over 3 minutes?
No, we need to transition.
Okay. Thank you very much.